let's keep doing some Laplace transforms. And one, it's good to see where a lot of those Laplace transform tables you'll see later on actually come from. And it just makes you comfortable with the mathematics, which is really just kind of your second semester calculus mathematics, but it makes you comfortable with the whole notion of what we're doing. So first of all, let me just rewrite the definition of the Laplace transform. So it's the L from Laverne and Shirley. So the Laplace transform of some function of t is equal to the improper integral from 0 to infinity of e to the minus st times our function of t, and it's with respect to dt. So let's do another Laplace transform. Let's say that we want to take the Laplace transform. Let's say we want to take the Laplace transform. And now our function f of t, let's say it is e to the at. Laplace transform of e to the at. Well, we just substituted it into this definition of the Laplace transform. So that is equal to, and this is all going to be really good integration practice for us, especially integration by parts. Almost every Laplace transform problem turns into an integration by parts problem, which, as we learned long ago, integration by parts is just the reverse product rule. So anyway, this is equal to the integral from 0 to infinity, e to the minus st times e to the at, right? That's our f of t, dt. Well, this is equal to just adding the exponents because we have the same base, the integral from 0 to infinity of e to the what? A minus s, e to the a minus s t dt. And what's the antiderivative of this? Well, that is equal to what with respect to t? So we're at, it's equal to 1 over a minus s. That's just going to be a constant, right? So we can just leave it out on the outside. 1 over a minus s times e to the a minus s t, and we're going to evaluate that from t is equal to infinity, or the limit as t approaches infinity, to t is equal to 0. And I could have put this inside the brackets, but it's just a constant term, right? None of them have t's in them, so I can just pull them out. And so this is equal to 1 over a minus s times, now what is the limit? We essentially have to evaluate t as at infinity. So what is the limit at infinity? Well, we have two cases here, right? If this a minus s is a positive number, if a minus s is greater than 0, what's going to happen? Well, as we approach infinity, e to the infinity just gets bigger and bigger and bigger, right? Because it's e to an infinitely positive exponent. So it actually, we don't get an answer. And when you do improper integrals, when you take the limit to infinity and it doesn't come to a finite number, the limit doesn't approach anything, that means that the limit, or actually the improper integral, diverges. And so there is no limit. No limit. And to some degree, we can say that the Laplace transform is not defined when a minus s is greater than 0, or when a is greater than s. Now, what happens if a minus s is less than 0? So if a minus s is less than 0, well then this is going to be some negative number here, right? And then if we take e to an infinitely negative number, well then that does approach something. That approaches 0, and we saw that in the previous video. And I hope you understand what I'm saying, right? E to an infinitely negative number is 0, or it approaches 0, while e to an infinitely positive number is just infinity, so it doesn't really converge on anything. So anyway, so if I assume that a minus s is less than 0, or a is less than s, and this is the assumption I will make, just so that I get, so that this integral, this improper integral, actually converges to something. So if a minus s is less than 0, then this is a negative number. E to the a minus s times, well, t, where t approaches infinity, will be 0, minus this integral evaluated at 0. So when you evaluate this at 0, what happens? T equals 0, this whole thing becomes 0, e to the 0 is 1. E to the 0 is 1, and we are left with what? Minus 1 over a minus s, and that's just the same thing as 1 over s minus a. So we have our next entry in our Laplace transform table. We have our next entry, and that is the Laplace transform. The Laplace transform of e to the a, e to the at is equal to 1 over s minus a, as long as we make the assumption that s is greater than a. This is true when s is greater than a, or a is less than s. Either way, you could view it either way. So that's our second entry in our Laplace transform table. Fascinating. And actually, let's relate this to our previous entry in our Laplace transform table, right? What was our first entry in our Laplace transform table? It was Laplace transform of 1 is equal to 1 over s, right? Well, isn't 1 just the same thing as e to the 0? So we could have said that this is the Laplace. I know I'm running out of space, but I'll do it here in purple. We could have said Laplace transform of 1 is the same thing as e to the 0 times t, right? And that equals 1 over s. And luckily, it's good to see that that is consistent. And actually, remember, we even made the condition when s is greater than 0, right? We assume that s is greater than 0 in this example. And lo and behold, here again you say s is greater than 0. This is completely consistent with this one, right? Because if a is equal to 0, then the Laplace transform of e to the 0 is just 1 over s minus 0. That's just 1 over s. And we have to assume that s is greater than 0. So really, these are kind of the same entry in our Laplace transform table. But it's always nice in mathematics when we see that two results we got trying to do slightly different problems actually are in some ways connected or the same result. Anyway, I'll see you in the next video, and we'll keep trying to build our table of Laplace transforms, and maybe 3 or 4 videos from now, I'll actually show you how these transforms are extremely useful in solving all sorts of differential equations. See you soon.